Hey everyone, today my lecture will be made and available only online due to the reason that I have another meeting and occasions tonight. So my lecture is recorded right now, so around the time of Thursday evening you will be able to listen and watch my lecture. Last time we looked at the signal and data encoding. We looked at a little bit of those, the algorithm last time, but I'm going to review those so you can follow up as I go through. I'm trying to get my pen here. It's not over. That's fine. Okay. So encoding techniques. One of the basic questions to you, why encoding? Why encoding is important, particularly to the wireless communication. My answer to you is in this way. In computers, encoding is the process of putting a sequence of data into a special format for efficient transmission. So technique of encoding is in essence to transmit data efficiently. When data is transmitted, there should be energy to push the signal out. So actually, so we need to show the voltages of the data that we want to send out. So depending upon the magnitude of the voltages at the receiver side, the data can be identified. Various techniques, algorithms developed. One of the techniques that you might hear from the movie is a Manchester. Remember that in World War II, I believe that is German soldiers and U.S. alliance, well actually UK alliance would like to fight, but as they set the D-date, all the secret information must be transmitted to alliance, but German technology may be able to catch our transmission. Therefore, they need to encode. And also, on the other hand, the UK would like to understand the communications made in Germany, right? So University of Manchester developed the encoding technique. Before we get to the Manchester algorithm, we will look at a few simple techniques. Okay, techniques that we can learn today can be used for storage efficiency improvement. If you want to store the data, then the data is not necessarily stored as is, but can be encoded and stored. So techniques for transmission will be the same as techniques for storage. All right, the simple idea for the encoding is this. So-called non-return to zero NRZ algorithm is a very simple technique. If you have a 1 bit of your data, then we can say that is a high value 1 and 0, that's low value. So that is a 0. You can simply consider this. The high value 1 is, for example, 5 volt. 0 means there is no voltages. Okay? So this is very simple. Another way is a non-return to 0 level algorithm. This is actually opposite to non-return to 0 algorithm. If there is a 0 bits, then as opposed to the low value, but in this case we want to put it in a high value. If there is a 1 bit, then low value of voltages. And a little bit more advanced algorithm from there is a non-return to 0 inverted, so-called NRZI. It's a little tricky from there. If there's a 0 bit, then we consider there is no transition at the beginning of an interval, and 1 means transition at the beginning of the intervals. And those are all non-return to 0 family algorithm. The algorithm developed after that is bipolar alternate mark inversion. Bipolar means that the voltage can be used not only positive range but also negative. So the voltage can be sent out from 5 voltages to -5 and more. This encoding technique that we learned today is to consider only one data sequence, but in the next class we'll look at, for example, in wireless communication, multiple senders would like to send together. Okay, presumably, let's say there is only one access point, but there are multiple users. Each user sends a different data. But data, the signals should not, data that you send should not be delayed. You do not want to wait until there is a turn, there is a time that you can, time available for you to use, right? So all the data, when the multiple data comes in to that electronic device, then they should be mixed together. So if you have 5 different senders, signals comes in, then you can simply think, oh, instead of 5 volt for one signal, maybe 5 times 5, then 25 voltages, or plus positive 25 to negative 25 voltages. In that range, the signals is transmitted. There's a bipolar AMI. Another algorithm that we will look at is Pseudo Ternary. It's similar to bipolar, but we'll look at that. Manchester. This is really sophisticated algorithm that we will look at. Little advanced from there is Differential Manchester. So we'll look at all these algorithms using examples. Okay. So okay, so we looked at this last class. I'm going to remind you of this. Let's say if we have data 10110010, then this data can be encoded into this type of signal, which means if there is a 1, then there is no signal. If there is a 0 bits, then there is a voltages. Okay, for 0 bits, high voltages. For 1 bit, there is no voltages. That is the case of non-return to zero level algorithms. Okay, and another algorithm that you might think is inverted of that, which means if we have the data 10110010, then if there is a 1 bit, which means there is a transition, and there is no bits, there is a 0 bits, then there is no transition. 1 bit, there is a transition. 0 bit right now that is a high value, and next one means because there should be transition, then transition from high value is from high value to low value, right? So it drops. And then there is another one, then there is another transition, therefore from current value to the transition, then low value to high value. And there is a 0, then stays the same, and 1, another transition, right? So at the end of this encoding, you might have 110, 11100, which is encoded value. 1 means there is a high value, low value, high value, low, high value, and low and low. So given data sets 1011, 0010, after the encoding in inverted way, the data will be 110, 11100. Actually, this is our representation, but in real communication, the 1 means high value transition, 0 means low value transmission. Okay, so a little more advanced algorithm, a little more advanced from there is bipolar encoding. In this case, bipolar, therefore, we have two polarized signals generated. If there is a data bit 1, then we will have some voltages, but halfway, not the full voltages, but halfway. But there's a polarized. So halfway, 1/2, and negative 1/2. Whatever the voltage it is, we want to reduce. We want to use half of those. If there is a 0 bits, then no voltages. Okay, so this is similar to non-return to zero inverted algorithm, but this is a polarized. So if you apply that to this data, 0, 11, 000, then as we looked at, to apply 0 level, unpolarized 0 level, then it'll be 1, 0, 0, 1, 1, 1, right? Given this data, 1 means here 1 means at the level at the this is a simply conversion, right? 0 bits will be turned to high value, 1 bits turned to low value, and so on and so forth. If that is inverted, then the 1 means there is a transition. See, there is a transition from 0 bits to 1 bits. There is a transition. from 1 to 1 there's no transition, therefore we put 0, and from 1 to 0 there's a transition, therefore we put 1, and then 0 to 0, 0 to 0 there is no transition, therefore we have 0 and 0. This is the NLZ I encoding technique. Bipolar encoding technique, it's very similar to NLZ I, but we want to use half value for the polarized fashion. So positive half and negative half. Once I use a positive half, next one will be the negative, alternatively. So one time positive and next time negative. And when it comes to another high value, then it'll be positive half, and next time high value, that will be negative half, and so on and so forth. Alright, this is the bipolar encoding. And another one is a pseudo ternary. One represented by absence of line signal, 0 represented by alternating positive and negative. So it is like this. 1 means there is no values. So if we have 1 bit, then there is no values, right? This is outside, right? We have 2 ones, there's no values. And for 0 values, it's alternating positive and negative. But it is a little extended from bipolar encoding. So if it comes half positive, half of voltages, and next one will be negative, followed by positive and negative. So it forms like this. Okay, so a little bit of opposite to this, but that is the case here. This guy is talking about some transition, but this guy is to look at the value only. So data value, if it is 0 bits, then alternatively half of voltages. 1 bits, no voltages. Alright, so that is what actually 4 of those, but I hold on. I'm going to minimize this, I'm going to minimize that, and what I did, here, and also part of that is assigned for you to do the implementation of this. Okay, using Python, I want you to implement a little bit of those, but you do not. I programmed this at my side. You do not have to be in this way, but I did a little more than what you could do in next few days for your homework assignments completion. So to do the Python, I'm going to bring it up. Python, I believe. Yeah, you have already some of the. I know you. We looked at Python, right, last time. So what I'm going to do is to bring up the code that I made. Let's see. good. And here, where is it? Program and encoding. Okay, so I'm going to bring up to Manchester also for the next exercise. So here, encoding a simple algorithm. A simple algorithm means, I'm going to show to you a little bit of those. What I did here is, if you can, you can, but if you cannot, you don't need to. For example, in our example here, the given data is a binary data itself, right? But my implementation starts from character. For example, your emails or whatever the data that you send. So I first convert the data into the binary code. Then usually binary code is a lot bigger than this. If you have 8 bits, then that is only one character. Okay, so if I say mercy, M-E-R-C-Y, then M 8 bits, E 8 bits. So 5 characters, each 8 bits. So 5 times 8, then 40 bits. So you have to work on the 40 bits of those, which looks a little nicer and challenging. But you could do more and more if you do this type of programming accomplishment. Okay, that's what I did. And then something that I did in, so you do not need to conversion if you do not want to, or if you do not have enough time. Don't spend much time on this. Those who are familiar with Python could do this. The basic idea, why I ask you to do this in the programming in real coding, is because in many cases, from my observation, and also we have track records that a few of our graduates are hired by top level companies and institutions, right? Those are all successfully hired with the work completion. Top level employers would not hire those who knows the concepts only, those who knows how to talk about, but they hire the people and students who had some experience, okay, programming experience. The reason they want to hire is because they want to make it, and from there they want to make a profit, right? Doesn't matter the level of degrees. When I graduated, even PhDs, they do not hire if PhDs cannot do programming by themselves. It happened since 20 years ago. And doesn't matter, I mean, mathematicians or engineers, scientists, they all should know, at least if they have, each one of you, if you invent some idea, then you have to prove it. How can you prove it? Not in theory, but in practice. So I want you to practice it. You need to show that it really works on computer. Otherwise, no one would like to buy it, right? So that is a basic idea. Those who do not have the strong background, don't be discouraged. There is nothing. It's too late. So I wanted to start at any time that you realize that you really need to learn you need to implement what ever the concepts you newly invented. Okay, it doesn't have to be strong and complete system, but any small piece of idea, if that can be implemented nicely, then you can present it to your interviewer. Then interviewer if interviewer is convinced, then there's no reason that you cannot be hired. Okay, we have so many such graduates already. So there's one thing, and the other two the modules that I imported in my program is the plotting. So actually, at the end, I want to draw the way that we looked at here in this here, right? So I made this is a step plots, and another one. This is the conversion from string to binary and binary to string. This guy call the iterative mode of string to binary and binary to string. Then they're all commented out. And I have NLZ encoding and NLZ L, so NLZ level encoding, and another one is NLZ I inverted encoding, and bipolar encoding, and then pseudo ternary encoding. This is the end of my program. So what I'm going to do is to run it. Okay, simply I can do control and enter key, then that is being entered, executed. Let's start from simple 8-bit data. 8-bit data should be encoded and transmitted. Transmission is not really discussed today, but next week. Supposedly, if you have 5 senders who would like to transmit the data together, then you need to put them in one signal, right? One signal is flying over the air, and at the destination, those 5 data should be fully detected. How? Yeah, that is the magic that we will discuss next time. So enter message. We can put any message. For example, oh, Mercy is so great in cybersecurity, but that's too long. So let's start with 1. Okay, let's say M, small m. Small m is not the same as big M in binary, right? So let's take a big M and enter. Quick, right? Energy encoding. Big M here, look at this. Big M is in binary 01001101. That is encoded. So 0 in NLZ code. There is a see here, look at the x-axis. There is 0, 1, 2, 3, 4, 5, 6. It's encoded that. So in NLZ, this is a given, right? 0, 1, 0, 0. So we have started 0, 1, 0, 0, and 1, 1, 0, 1. So start from here, 0. This is a given data. If we encode this given data using NLZ, then this is the outcome. Voltage 0, 0, 1, 1, 0, 1. Just a little bit. Use this one. Okay, this is energy L. This is opposite. This is energy I, which means if you have that same M, one means there is a transition, right? Energy I. So there is a transition because we have a 1, there is a transition, and there's if there is no transition in 0, and there is a transition, so there is a 1, no transition, we put 0, and so on and so forth, right? So these whole things will be displayed here. For example, enter message M, energy, text after energy, then we have that, energy I, energy 1, I do not know why it stops, but so that is that, and another, okay, bipolar encoding, so that I have a bipolar. I entered M, but after it is encoded, it will become K. This is real tricky, right? So I want to send the M, but it appears if I this is a binary code. If I recognize this binary code, then that will be K. So very nicely, it is encrypted also somehow, right? According to that algorithm. So this encoding technique is not just the signal generation, but a little bit of encoding. So if you add the little bit of encryption techniques, cryptography here, then very nicely it'll be scrambled, right? So this is a bipolar. What it does here is that there's a halfway, right? This is a 0. Look at this, 0, and positive half voltages and positive negative, and then in 0 because there is no a transition. If there is a transition, then from negative half to positive half, there is no transition, so it will be 0. So there is a transition. After positive half, it will be negative half. So this is in the middle. That is a 0 voltages, low voltages, and above that is half, and below that is a negative half. This is a bipolar encoding. And then finally, pseudo ternary encoding. Similar to that, but if there is a 1, then there is no voltages, right? Whenever we have a 1, then there is no voltages. 0, then we can do positive half and negative half, like that. All right. So in that way, it is done. And finally, if we apply pseudo ternary, then it'll be scrambled to number 2. In this case K, in this case K. Some other cases you cannot recognize what it is, right? Because what happens here is that ASCII code, the code that we understand in English, requires low ASCII, which means only first 7 bits are enough to represent all kinds of characters that we understand, including some special function keys. Beyond that, if we include 8th bits, okay, then it is much more than that. Not all of them that we can understand. Some of them only available as some shape, okay. So in old long time ago, when there is no Windows systems available, more precisely before we have TK actively used, then anything that you want to draw on your terminal, then you need to use the ASCII code from your default computer systems. In that case, you might have some other characters that we cannot understand, but the character that exists anyway. Okay, so let's try a little more than that. Let's say enter messages. We can say mercy. If we do that, then it gives you mercy total. Then it is this long binary code. NLG encoding is like that, and NLGL encoding, if it is high voltages, and if there is a high value, 1 in binary. Look at here, this is a binary code, right? So I would say this is data and this is voltages. I'm going to change that. So so this is NLGL, this is NLGI, this is a bipolar. This is in the middle, and this is half positive half and negative half voltages. And then pseudo ternary encoding. Let me see if I can change somehow here. Okay, so Y level, this case is lower. So what I'm going to do here is I'm going to change this to data. Okay, so save it. If you look at this, for example, text after pseudo ternary, then the encoded data is this. See, this is what I'm talking about. And text after bipolar encoding, then encoded, the mercy is converted to in this symbol. It's not really mercy, right? It's the same as this. And another unrecognizable characters, another unrecognizable characters, right? Given this mercy. Try one more. What did I ask you to do? I think I asked you to do, I don't remember on your example, but let's say some CSCC, Cyber Security Program, CSCC. Okay, let's put all small and enter. Then there's a CSCC. We have this is data, okay, and this is voltages. This is much better, right? And then here we have a data according to NLG data given like this, then encoded in this way for the message CSEC. And another inverted case is this, and this is bipolar. This is pseudo ternary. All right. Let's move further. So challenging. Manchester. All right. So this is Manchester. Manchester used 2 bits of signal per 1 data bit. If we have 1 data bit 0, then encoded signal will use 2 bits. So 2 signal bits per per one data bit. If you have 0, then transition from high to low in the middle, like this, in the middle of an interval, 2 bits interval of the signals. You could do not only, in this case, at least 2 bits, but it could be longer bits. Someone might ask, oh, 1 bit compared to 2 bits, then it's a waste of resources. No, it is not the case. Look at the frequency of the transmission bandwidth. Let's say 2.4 gigahertz. Around there, one channel, let's say 20 megabyte, 20 megabyte, that is the bandwidth that your signal will occupy at a particular time, particular situation. Out of 20 megabyte, 1 bit, 2 bits, it's not really big issue. And therefore, the concept that we will look at next class is spread spectrum. Spread spectrum would like to, for example, 1 data bits, we use in reality 120 chips, 128 chips. One chip will be 1 bit, at least, maybe 2 bits. In order to send the 1 data bit, the bandwidth that accommodates is 128 bit chip. We call that chip. Okay, there's a sequence of characters. But anyway, so we'll get that next time. So 0 means from high to low, 1 means from low to high, and so on and so forth. So if we have 0, then high to low, 1, then there's a low to high, and so on and so forth. So what is the advantages of this? It's a synchronization. It's improved. What do we mean by that? Thing is this: if you use only, let's say, in the previous somewhere here, if we have one long high voltages, then you do not know how many data of ones, because the high voltages comes continually for some time period. But if you have this half, then you will know, right? Actually, this is one data bit, this is another data bit, another data bit, another data bit. There is no way that it continue to have the same high value or same low value, right? That is the advantages of using Manchester. This is a Manchester, and there is a differential Manchester encoding. 1 means if there is a transition, 0 means 0, then we simply follow the previous bit. Okay, so this is the most sophisticated algorithm. See here, if you have 0, then it follows whatever. 1, then there's a transition, right? Like Manchester transition from low to high. And there is a 0, then 0 means you follow the previous. Whatever it is, you follow. Previous ones is low to high. So you simply low to high. 0 means it's previous, so low to high. And 1 means there is a transition. Transition from low to high, therefore high to low, there's a transition. 1 means there's a transition. So opposite. 0 means follow the previous. If it is a low to high, yes, a low to high. 1 means transition, high to low. 0 means follow the previous, so high to low. 0, follow the previous, high to low. Okay, this is a Manchester encoding. So we looked at two versions of Manchester encoding algorithms. So we will look at that how it works. Okay, I'm going to change the legend. Instead of voltages, I'm going to say data, and then next one will be the voltages. Yeah, this one voltage, the other one is that. Alright, so I'm going to run Manchester. So let's start with the same one. That's M. Okay, Mercy. See what happens. M then is a Manchester. So each of it is a 0, 1, 1, 0, 1, 1, 0, 1. That is a data sequence, data messages. So for example, 1, this is 1 entire from here there, then 2 bits used. So 1 means whatever we previous will be changed, right? High to low, therefore we change low to high. And then there is another 1. So low to high. I think there's just a mistake, right? Low to high, therefore should be high to low. There should be a transition. High to low, and 0 follows the previous. So high to low, and 1 means we need to change it to low to high. Change it that back. It's a little mistake, but wait a minute. Oh, that is a differential. I made a long explanation. I'm going to go back to wrong explanation. Text after the Manchester, it'll be this. Differential Manchester, that, right? So let's try the same one. So Manchester is, let's see here. Manchester encoding means 0 means transition from high to low, 1 means low to high. Okay, that's simple. There's a Manchester. 1 means low to high, 0 means high to low. Low to high, if there is a 1. If there is a 1, a low to high. If there is a 0, high to low. If there is a 1, data bits 1, then there's a low to high. Data bits 1, therefore there is a low to high. Data bits 0, therefore high to low. Data bits 1, so low to high. It's not a mistake, this is correct. This is a Manchester encoding. Differential Manchester is the one that I try to do. Here is the 1, then we need to have a transition. Previously 0, if that is a shape like this, then we convert that to, we make transition, so low to high. Because there is a 1, so another transition, high to low. If there is a 0, then follow the previous, high to low, repeat it. If there is a 1, then transition, so low to high. If there is a 1, transition, high to low. If there is a 0, then repeat. High to low will be repeated here. And then there is a data bits 1, therefore low to high, I mean transition. Okay, that is differential Manchester encoding. So if we do that in a little more longer messages. For example, Mercy is good in side-sec. Oh, that's a long, right? So busy signals that may be displayed. Wow, it's almost so ups and down like this, almost red, and similar to that. That's too low. So this is converted. Let's try it. No. Let's run. Let's say is simply excellent. Excuse me, excellence. I'm going to put capital E, excellence. Okay, excellence. This is excellence. Data bits, and this is a voltage signal, voltage of the signals. According to Manchester encoding. This is differential Manchester encoding. Okay, this is the data that we looked at. Some of the data. So ones and zeros, almost the ones. Too much fluctuations. Okay. So, oops. We've done almost. So this is an exercise that I want you to do. Let me see if I have an answer somewhere. I do not have an answer. This is an exercise that I want you to do. And this is, oh yeah, I said the sick. This is a homework assignment that I already posted. So this is a given message so that you can encode this message using each one of these. So I want you to do that manually, okay, and also Python implementation as much as you can, okay, as much as you can. But that's my utmost expectation. All right. Okay, this is it for today, and I'm going to see you. Yeah, about an hour lecture, but I think you need to take a lot longer time to understand. So I wanted to repeat and reply and hold up at some points if you do not understand, and I want you to see also some of the coding list that I made if you are interested in. So I'm going to show to you this Manchester also. Step plots remains the same, that I use the same ones. Yeah, Manchester encoding. This is Manchester. Because for data, one data bits, I'm going to use two signal bits. Therefore, I append if one means 0 to high, else high to low. That way I can manipulate. And differential Manchester, little more than that, right? This is a positive and negative values, and a little more than that. So I want you to practice. This is a little tough, right? I'll see you next week in class at Mayor Hall. Have a great day. Bye bye.